Hi, and welcome to my software workshop for the SAS Explore Conference. My name is Jeffrey Thompson. I'm a Senior Analytical Training Consultant at SAS, and my software workshop is on advanced tips and tricks for Model Studio. Just a little bit about myself before we jump further into the workshop. I've been a user of SAS since the early 1990s as an undergraduate math major, and I've been employed by SAS since 2010. In my early career, I was a professor in the Department of Statistics at North Carolina State University, where my research and teaching duties focused primarily on traditional statistics. But since I've been employed at SAS, my career has focused on predictive modeling and data science applications. All right, let's jump into the workshop. Certainly we're going to be spending some time in the computer using Model Studio, but we're going to have a little bit of discussion along the way also. First, let's just start with an outline of the workshop. The first section is the simple outline, followed by 3 sections. Section 2 seems like a hodgepodge of almost independent topics, but there is a method to my madness, and we'll see it when we get to the next section. We'll be covering feature engineering, model interpretability, and then something known as the ensemble trick to assist with model interpretation. In section 3, we'll be discussing how external models from SAS Viya can be used within Model Studio. We'll talk about SAS 9 and SAS Enterprise Minor models, as well as open source models and how they can be used within Model Studio. And we'll see a couple of demos there. And in the final section, we'll see how to create custom model assessment plots in Model Studio. All right, so without any further ado, let's get to it. So the next section, again, feature engineering, model interpretation, and the ensemble trick. Let's kind of connect these 3 topics together and build up to what the final punchline in this section is. You're probably familiar with feature engineering. Feature engineering is the idea of creating or selecting new input variables for your model. And they can be grouped into a couple of different subsets. In feature construction, we create new features by doing brainstorming, aggregation. These are transformations, but not really extremely complex mathematical transformations. It might be something like taking date of birth and transforming that to age. In feature selection, we're simply reducing the number of input variables that we have. So we're not creating new ones, but we're looking at a subset of those that we already have. Feature extraction is what we're going to be talking about. It is similar to feature construction in that new features are created through transformations, but these are often more complex mathematical transformations. One of the things that we typically think of giving up when we do feature extraction is interpretability. We often lose interpretability of our model because of the advanced transformations we're considering. So there is a pre-built node in Model Studio to do feature extraction, and the feature extraction node has a couple of different types of transformations that are available. Principal components analysis, probably the most common one on the list, singular value decomposition, robust principal components analysis, and autoencoders. And we'll be using principal components in our demonstration, probably because it's the most widely known of the feature engineering methods that the node has, and therefore I won't need to spend a whole lot of time talking about it. Principal components are constructed as mathematical transformations of the input variables. Each principal component is a linear transformation of the variables, and each principal component is constructed of all of the variables in the data set. And mathematically, principal components has to do with transforming higher dimensional data into lower dimensions. A more digestible interpretation of a principal component is to think of your data as just a cloud of data. The first principal component is the longest axis of variation through that cloud of data. It's accounting for as much variation among the input variables as possible. The second principal component is always orthogonal or perpendicular to the first, and it accounts for the second largest amount of variation within that cloud of data. In addition to engineering features, we might also be interested in model interpretability. Many machine learning algorithms themselves are black boxes, but SAS Viya does provide some capabilities, some additional tools that can help gain insight into the model. The methods or techniques are listed on the right of this slide, things like variable importance, partial dependence, individual conditional dependence plots, and so on. And what that actual method solves, or what question it answers, is on the left. To keep our demonstration simple, we'll be doing model interpretability using partial dependence and individual conditional dependence, or ICE plots. Model interpretability is done directly through the model node itself. You just turn on a couple of properties and select what model interpretability plots you want to look at. But if you look at the process flow here, the pipeline on the right of the slide, you see that we have some variable transformations done before we build the model. So if we transform variables and those transform variables are used within the model, then that means model interpretability would be based on those transform variables. And if the transformations themselves are not interpretable, well, then we have not gained anything by doing the model interpretability. So this is really the punchline for the final section. We've tied a few things together. If you generate new features and use those features in your model, and if you do model interpretability with your model, the interpretation might fail. So the ensemble trick is simply to take one node, the ensemble node, connect it to your model, just one model. That means the model is essentially recreated. We're not changing anything when we ensemble just a single model. The benefit is the model interpretability plots will be performed on the original inputs. All right, let's go to our first demonstration of the workshop. Now, to allow the workshop to go a little bit quicker, I've already completed the first couple of steps in the demonstration. When you redo this on your own later, just start at step 1 in the demo, and after a short while, you'll build and do a couple of steps to get up to where I am now. So you will start at step 1. I'm actually going to start my demonstration at step 15. What I have done already behind the scenes is create my Model Studio project. I loaded my appropriate data set into memory and loaded that data set into the project. I changed the partitioning strategy for the project. I defined a variable churn as the target. And then the very last thing I did was I used a couple of the input variables based on business knowledge. I set their role to rejected. And again, that takes me up to step 15 in the demonstration. So in this application, we're working for a telecommunications company that is trying to predict which customers might be candidates for churning. So we're trying to predict the probability of churn based on demographic, prior usage, variables, and so on. I've gotten things started, so that means from where I am, I'm ready to go to pipelines. And let's go ahead and do a little bit of work. Even though we don't need to impute before building a gradient boosting model, we might build other models where imputation is important. So in this pipeline, we're going to start with imputing for missingness. On the data node, I'll right click, add child node, pre-processing, and imputation. I'm not going to talk about the imputation node. It is assumed that the participants in this workshop are familiar with predictive modeling as well as Model Studio. So I'm going to do my best to just focus on the tips that we're teaching you here as opposed to the other details. After the imputation node, let's go ahead and build a model. And for this demonstration, we'll do gradient boosting. So go back to the imputation node, add a child node, this time from supervised learning, and gradient boosting. Now, suppose we're in the scenario where I want to interpret the gradient boosting model. Gradient boosting models we don't necessarily think of as being highly interpretable, so let's use the SAS Viya model interpretability features to gain some insight. So with the gradient boosting node selected in the properties pane, I'm going to scroll a little bit down to the bottom. Under model interpretability, I'll expand global interpretability and local interpretability. And again, to allow the demonstration to move along pretty quickly, I've selected 2 of these model interpretability features to explore. We'll do PD plots and ICE plots. Make those 2 selections. Then we could either run the entire pipeline. I'll just go ahead and run things from the gradient boosting node, right click and run. All right, we've got our green check mark, so the results are ready. Let's take a look at results of the gradient boosting node. Right click and go to results. Again, I'll assume that attendees are familiar with Model Studio already. When we build models across the top, we see a couple of tabs. The first is called Node, the second is called Assessment. The third tab for Model Interpretability is only there if the Model Interpretability features are turned on. So we see some results from the node. If we are interested in model assessment results, they would be available both graphically and numerically. And here is the model interpretability items. Going kind of quickly here, for the partial dependence plots, you see that it might be based on numerical and categorical variables. And essentially what you're looking for here, or what is shown, is the overall relationship between one of the input variables and the predictions. So if we're looking at current days suspended, we're looking at current days suspended plotted against predicted values. And certainly it appears that there is a positive relationship between current days suspended and the probability of churn. And that seems to make sense. The more days your services or a customer's services might be suspended, the more likely they might be to churn. The ICE plots, which also contain the PD plot within them, is similar to the PD plot, except instead of aggregating over everything, we're also getting similar plots for individuals from the data set. This allows us to look for things like interactions or the differences between individuals within the data set. What we see from the PD and ICE overlay plot for current days suspended is, although the lines are not always the same for all cases, we do see an overwhelmingly positive pattern or positive relationship. It doesn't appear that there's obvious interactions between current days suspended among any of the individuals in the data set. All right, let's suppose we want to generate some new features and add them to the model in an attempt to improve the model performance. I'll close those results. I'm going to add a feature extraction node between imputation and gradient boosting. For those that are not maybe completely familiar with Model Studio, here's a little trick in how I can add nodes. If I want to make sure that my feature extraction node is between gradient boosting and imputation, I can add a parent node to the gradient boosting node. So I'll right click on gradient boosting, go to add parent node, data mining pre-processing, and we want feature extraction. First thing I'm going to do is change the method for the feature extraction node to be principal components. So in the properties panel under feature extraction method, let's change that to principal components analysis. I'm also going to rename the node. So if I right click on feature extraction, I'll select rename, and just to keep things a little bit more orderly, we'll rename that node PCA so we know what we're getting from it. I'll click OK. I'll allow the users to investigate the properties of the node on their own. Let's go ahead and run the PCA node. Right click and run. I'm not going to spend too much time talking about the results. We're not here to get a lesson on principal components analysis. We're just using them in the context of a bigger trick. All right, we've got our green check mark, so the results are ready. I'll right click the PCA node and go to results. Okay, so results are ready. We're looking at the results of the PCA node. What is that final punchline? Well, how many principal components were selected? We can see that from the eigenvalue plots graph. Notice that vertical line indicating the number of principal components selected is 20. Maybe we were interested in how much variability is explained by our 20 principal components. We can go to cumulative proportion eigenvalue and see that about 62% of the variation in the data is explained. Now, of course, we could always change the number of principal components if we wanted to account for more variation within the data, but for the purpose of this software demonstration, 20 principal components will be fine. Let's see what exactly is generated from this node. Let's see the new variables that will be passed on to subsequent models. I'm going to click the tab at the top for Output Data. I want to view the output data. Let's save a little bit of time by enabling sampling. And how about we just look at 10% of the rows? All right, the output data is now visible. We see any of the original data that was in the data set, the input variables, the unique identifiers, and so on. And the newly generated features are going to be at the right. And if I scroll over enough, there they are. PC1, PC10, PC11, we would have 20 new columns for each of the 20 principal components generated. All right, let's see how these principal components are going to affect our model interpretability plots. Let me close those results and let me run things just from the gradient boosting node. All right, we've got our green check mark. The run is complete. Let's look at the results of gradient boosting. And to see the punchline, we'll go straight to the Model Interpretability tab, where you can see the model interpretability plots are now based on the principal components, at least for the interval measurement level input variables. Categorical variables were not replaced using the principal components, only interval variables. So we do see that for the PD plot, 2 of the principal components are used. And we see that the relationship between PC10 and the predicted outcome is positive and almost linear, but we don't have the ability to interpret PC10 itself. So by generating features and using the model interpretability in the model itself, we've lost the ability to gain insight. So the final part of the demonstration is the final trick using the ensemble node. Close the results. We'll go right back to gradient boosting, right click, add a child node. Ensemble is considered post-processing, and we'll select the ensemble node. Now again, ensembling a single model does not change the model itself in any way. The only advantage here is in the model interpretability plots. We do need to make sure that we turn on the model interpretability methods. So for the ensemble model, make sure that node is selected. Towards the bottom of the properties for post-training properties, expand global and local interpretability. As we did before, select PD plots and ICE plots. And again, I think rather than running the entire pipeline, I'll just run the ensemble node, right click and run to save a few seconds. All right, we've got our green check mark. The results are ready. So again, if we compared the performance of the gradient boosting node and the ensemble node, the performance between these two models would be the same because they are in fact the same model. Let's take a look at the interpretability from the ensemble node. Right click on ensemble and go to results. We'll go directly to the model interpretability tab and notice now that the PD plot is on the original input variables and the same with the PD and ICE overlay plot. So even though the model itself contains uninterpretable generated features, by using the ensemble node, we are still able to gain insight into that model using the original input variables by making use of that ensemble node. All right, let's close the results. So we'll be ready for our next demonstration when we return here. Let's go back to the slides for a little bit more discussion. All right, the next section is on using external models in Model Studio. Just because you use Model Studio or live in a Viya world doesn't mean that all of the algorithms or all of the models that you're going to be using need to come from SAS Viya. One of the huge benefits of SAS Viya is how it is interoperable with other systems. It simply plays nice with other analytical tools. So let's discuss some of the external models that we might use in Model Studio, and then we'll do some quick demonstrations. So there is now interoperability between your traditional SAS 9 programs and procedures and SAS Viya. Not only are some of the SAS 9 procedures CAS enabled, but the data steps are as well. So that means one SAS program can actually take advantage of both the SAS 9 as well as your SAS Viya engines. In addition to the interoperability between those two environments, we are giving you, or in other words, SAS is giving you many legacy procedures to use in SAS Viya. There are SAS Stat, SAS Enterprise Minor, and even SAS High Performance procedures that are given to customers with a SAS Viya license. So again, you can use these external modeling algorithms within Model Studio to build models. The way that we're going to build these models is by using the SAS code node. The SAS code node is considered a miscellaneous node, and the SAS code node is the trick for using or for building SAS models not built within SAS Viya. So SAS Stat, Enterprise Minor, High Performance procedures all would be using the SAS code node. And of course, anything that you do within SAS code, you can do within the SAS code node, not just build models. You could create customized scoring code, modify variable metadata, manipulate existing data sets such as transforming or generating new features, and so on. On the left-hand side of the slide, you see the properties panel for the SAS code node. It's pretty slim. One of the main features is the Open Code Editor button. When you click on that button, that actually opens the code editor you see on the right of this screen here, where you can enter training code, scoring code, and you can also make use of macro variables to assist in your program. All right, we are actually only going to take a look at one type of external SAS model, and we're going to look at a SAS 9 model, and we'll bring that into a Model Studio pipeline. We'll be able to work with the same pipeline we did before, so I don't need to create anything new. I do want to take advantage of the imputation, so I'm going to add my SAS code node after the imputation node. I'll right-click on imputation, add child node. SAS code is considered miscellaneous, and SAS code. Again, just to be accurate, as we did before, I'm going to rename that new node. I'll right-click on the SAS code node and go to rename, and I'm going to call it SAS underscore stat underscore reg model. Seems a bit long, but that's because I do know what type of model we're going to be building. We're going to be building a regression model that comes from the SAS stat procedures. So the name of the node will be SAS stat reg model. Click OK to save the name. Before I bring in the code, what I might want to do is move this node to the supervised family. That way, all of the model assessment information would be provided for me. So on SAS stat reg model, I'm going to right click. I'll select move, and I'm going to move that to supervised learning. That'll change the color of the node to purple, indicating it's in the supervised family, and it will connect the node to model comparison. All right, let's bring the code in, where I'm not going to explain the code line by line, but I will describe the major components, or at least the heart of the code, if you will. With the SAS stat reg model node selected, I'm going to click Open Code Editor. And I want to enter my code into the training code window. We've got it pre-written for you. We'll navigate to it and bring it into the window or import it. So I'm going to put my cursor into the training code window first. Once I know my cursor's there, I'll select the Load Source Code File button. And then I'm going to need to navigate to where that code is found. And it looks like my computer opened up in the place I need to be, but let me navigate in case yours opens up someplace different. It is in the demonstration. We need to navigate to the D drive, D, then the workshop folder, WinSAS, then into the folder ADML. So I'm at D, workshop, WinSAS, ADML. And the program that I want to open is called L05 SAS Stat Reg Model .SAS. I'll highlight and click open. For those of you that are SAS coders out there, this looks familiar. This is good old-fashioned, everybody's favorite proc logistic. Notice we are using some of the macro variables to help us. So for calling the data, we're using ampersand DM data. In the class statement, we're using the macro ampersand DM nominal input. And again, those macro variables would be available from the left. We're also calculating some fit statistics for the model also. Pretty simple code. Again, remember this is SAS 9, but we're running it within Model Studio. I'm going to save the code. I'll close the window. And then let me just run that modeling node. So SAS stat reg model, right click and run. All right, we've got a green check mark. The results are ready. Before I open the results, I will say that we could have run the model comparison node and compare the models there, but that's not really the exact purpose of this workshop. I'll leave the model comparison up to you if you want to do that on your own. Let's focus on what the tips and tricks of the workshop are. So SAS stat reg model is complete. Right click. We'll go to results. And again, I'm not going to spend a lot of time here. We see the two tabs at the top, node and assessment. We did not ask for any model interpretability to be constructed here. So under the node results, we see the code, some of the generated score code, and the output of the underlying procedure. For model assessment, we could click the assessment tab and see graphical and numerical measures of model performance. All right, let's close those results. And still within this same section, but now let's talk about interoperability between open source models and Model Studio. So right back to the slides. And the interoperability between open source tools and SAS kind of works both ways. What I mean by that is you can be living in a SAS world and make use of some open source models within the SAS world, or you might be living in the open source world where you're making use of SAS procedures while living in the open source world. So the first scenario I illustrated, which is what we're going to be doing, is illustrated on the left-hand side of this slide. We are SAS users, we're comfortable in the SAS environment, but we know there are open source tools that are available to help us out as well. So within our SAS environment, specifically within Model Studio, we might be able to make use of Python or R for open source integration. In our demonstration, we'll just build a Python model. By the way, we do offer advanced training on all of these. So if you are a typical open source user and you want to see how to call or make use of SAS programs within the open source world, although it's not covered in this workshop, we do offer training on it. Just like the SAS code node, the open source code node is considered a miscellaneous tool. So it is a specially designed node. You're obviously not using the SAS code node here because you're not building SAS code. The open source code node is currently designed to work with Python or R code. There are some requirements such as where you're installing Python or R. The open source models cannot be part of an ensemble. They cannot be registered or published for scoring directly from Model Studio. And there are some other items you might want to be careful about, such as imputing for missing values. Open source models might handle missing values differently than SAS, so it's a best practice to impute before building open source models. The open source node is pretty straightforward. You see the properties pane on the left. In addition to selecting the language, the next most important property is the Open Code Editor button. And very similar to the SAS code node, that button actually opens up a code editor where you can import or type in your own code. Again, we'll just illustrate a Python model in this next demonstration. Let's get to it. We'll be able to make use of the same pipeline. I definitely want to make use of the imputation node, so I'm going to add my open source node right after imputation. Right-click on imputation, add child node, miscellaneous, and open source code. First thing I'll do is I'll rename the open source code node. Right-click, rename, and we'll call this Python Forest because we'll be building a forest using Python. I'm not going to actually illustrate this, but if I were to run the code in the node as the node is in the current state, the code would run successfully, but I would not get any model assessment information. Just like we did for the SAS stat reg model, I need to move the Python Forest node to the supervised family so that Model Studio generates all of the model assessment information for me. Again, the node would run successfully if I didn't move it. I just would not get the appropriate assessment information. So let me go ahead and make that move now. I'll right-click on Python Forest, move to supervised learning. Let's get that out of the way first. We're going to change a couple of the properties. We'll import the code and then make one final change before running things. With Python Forest selected, verify that the language is in Python. That should be the default for that property. Expand the property for data sample. Expand the property for data sample. Towards the bottom of that sub-property list under data sample is include SAS formats, which is selected by default. I'm going to turn off or deselect that property. All right, let's bring in the Python code. With the Python Forest node selected, I'll click Open Code Editor. And we want to bring this into the training code window. So put your cursor in the training code window. Click that Open Folder button. You shouldn't need to navigate, but if you do, the location is D, Workshop WinSAS ADML, and we want the Python code L05 Python Forest.py. Highlight and click Open. So we import the necessary packages at the top. We manipulate the data a little bit. Where is the heart of the code? Again, we're fitting a random forest model using the ensemble.randomForest classifier package. We get some variable importance information, and that is the Python code. Let's save it, and we'll close it. And one more property to select, and this is important if we wanted to compare this model with other models. So if we want to do model comparison, this next step would be required. I'm not going to do any model comparison, but let me go ahead and select that next step anyhow. Use output data in child nodes. You might want to almost consider that a best practice when using the open source code node to allow the results to be passed on and used by other nodes. So I've selected or turned on use output data in child nodes. All right, let's run the Python Forest. Right click and run. All right, green check mark, so we've got our results. Right click on Python Forest and go to results. Similar to the SAS stat reg model, we see the two tabs across the top. The Node tab is selected by default where we see the Python code. We see the output. If we were interested in model assessment, again, both graphically and numerically, it would be available on the Assessment tab. I'll close the results. And again, if we were interested in model comparison, we could run the model comparison node and compare all the models that we've got in sight. But again, that's not the purpose of this demonstration, so we'll stick to our purposes here. All right, let's go ahead and return to the slides for our final section. All right, what about creating custom graphs in Model Studio? We know that Model Studio generates several graphing tools for you automatically, but what if we want to generate a custom graph? Well, no problem, we can do that. Here are two common model assessment plots that are generated automatically. In fact, they're families of plots. We have multiple lift report plots that are available. Those are usually based on response type metrics. So for example, cumulative lift, and we've got the ROC reports, which essentially gives information such as true positives and true negatives. But what if we wanted to generate a custom plot? The ROC chart, for example, is based on true positive and true negative rates. What if we wanted to look at those values separately, not combined within the ROC chart? Well, we can do that using the SAS code node. We've already seen in this workshop the SAS code node being used to build a model. And as I said earlier, anything that you can do in SAS code, you can do using the SAS code node. You can generate features, you can explore the data, you can build models. In this case, what we're going to be doing is we're going to be generating some new plots. Just as we saw before, our SAS code is going to make use of some of the macro variables. What we're highlighting here is more of an exhaustive list. So the full list is available from the code editor window by clicking a shortcut button. All right, let's jump into our final demonstration. Again, we'll be able to use the same pipeline. The first thing we're going to do, though, is take a look at the default model assessment plots. Let's go back to the gradient boosting node. I'll right-click on gradient boosting. It's already been run. Let's go to results. Assessment plots are available on the Assessment tab. And there's the two same family of plots we talked about on the slides. Lift reports, which is showing cumulative lift by default, and ROC reports showing the ROC chart by default. Well, let's pull apart some of the information in the ROC report. Let's plot true positive, true negative, as well as false positive individually, each against the cutoffs. I'm going to close those results. We're going to connect a SAS code node after gradient boosting. Right-click on gradient boosting, add child node, miscellaneous, SAS code. And again, I'm not going to explain the code line by line. I'll kind of give you the highlights. In the new SAS code node, make sure it's selected. I'll click Open Code Editor. We want to enter this code into the training code window, so make sure your cursor is in the training code window. And we'll load source code file again. Click that Open button. And the code that we want is at D Workshop WinSAS ADML. D Workshop WinSAS ADML, and we want L07 underscore ADDL model assess. L07 underscore additional model assess. Select that code and click Open. So at the top, we're getting some of the predicted values and the levels of those, the target variable that's needed. The heart of the model is proc assess, which is used to assess the model and provide some of our fit statistics. Then we're using sgplot to plot some of the assessment information. Notice there we're looking at 4 different plots being generated for us. Sensitivity versus cutoff, specificity versus cutoff, false positive rate versus cutoff, and accuracy versus cutoff. And then we're also generating just some reports of those same values. All right, I'm going to save that code. I'll close the window. And let's run the SAS code node. All right, green check mark. Results are ready. I'll right-click and go to results. The reports that were generated or the tables of the values are provided at the bottom of the results. The 4 plots that we mentioned are here at the top. Sensitivity versus cutoff, specificity versus cutoff, false positive rate versus cutoff, and accuracy versus cutoff. Now the ROC chart itself is based on sensitivity and the false positive rate, or 1 minus specificity. So the ROC chart is technically using the information in the plot in the upper left-hand corner and in the lower left-hand corner. And we want to be a little bit careful about how we interpret these. We might almost want to read the cutoffs from right, or the large cutoffs moving left to the lower cutoffs. If you think of the ROC chart for both sensitivity and the false positive rates, they both start at 0 and then they both end at 1. So for very large cutoffs, say a cutoff of 1 or 0.9, we typically expect small values for sensitivity. And that's what we're seeing here for the larger cutoffs. Notice that sensitivity starts at 0. As our cutoff decreases, as we get deeper and deeper into the data, then the sensitivity is approaching the value 1. So again, just got to be a little bit careful. Based on how we've asked cutoff to be provided on these plots, it's almost as if you're reading them from right to left. Specificity might be useful to look at. Remember, the ROC chart plots 1 minus specificity, or the false positive rate. And again, for large values of the cutoff, false positive rate tends to be small, and it tends to approach 1 as we get deeper in the data. Exactly what we're seeing here. At a cutoff value of 1, the false positive rate is 0, and the false positive rate increases, approaching 1 as the cutoff decreases. So a little care in interpreting them, but those are plots, again, not available for free anyway, or at least from an existing node. Within Model Studio, we generated them using our custom code. Some of the tables of values or some of the reports are at the bottom. So the different statistics based on the different cutoffs. There's the code itself, and there's the output from proc assess. Thank you for attending my software workshop. By the way, I don't think I've said this yet in the workshop. This material actually came from a course that we offer, Advanced Machine Learning in SAS Viya. So if you liked what you saw here, if you want to see more details on this, or if you want to see more advanced tips and tricks in Model Studio, consider taking that class, Advanced Machine Learning using SAS Viya. Again, my name is Jeff Thompson. My email address is on the board, jeff.thompson@sas.com. Please email me if you have any questions. And I hope you enjoy the rest of the conference. Thank you for attending my workshop.